Dear children, hope you are all doing well. Today's topic is mole concept, Avogadro hypothesis and applications of Avogadro law. Dear children, welcome to today's session. Let's learn the first topic, mole concept. Watch and learn.
Let's say you're going grocery shopping and your shopping list is 3 kg potatoes, 2 liters of juice and 1 dozen oranges. Now, what are these things in your list? The kg, liter, dozen? That's right. They are units. Units that we use in our everyday lives to measure the quantity of things. But now suppose I add to your shopping list 1 mole of salt. So do you know how much you need to buy? Do you know how much is 1 mole? Now don't go to the store and ask for 1 mole of salt because it's not an everyday unit. They're going to get confused. It's the chemistry guy's unit. And that is the one goal in this video, to really understand how much is 1 mole. And then we'll finish off with our top 3 exam-oriented questions on this topic. Do you have an idea how much is 1 kg of salt? Next time when you go grocery shopping, you can check the salt packets. Usually it says 1 kg. Do you know how much is 1 gram of salt? Let me show you. This spoon contains about 1 gram of salt. But the question is, how much is 1 mole of salt? 1 mole is defined as the molecular mass in grams. Let's break down this definition. Molecular mass is the mass of 1 molecule. And the substance here is salt. So to calculate the molecular mass, we need the molecular formula. So what's the molecular formula of salt? That's right, it's NaCl. So if we want to find the molecular mass, I need to use the atomic mass of sodium and chlorine. And they are 23 and 35.5 respectively. But I'm going to approximate chlorine as 35. So the total mass of salt is 58. Now this is the relative molecular mass. We need to take the molecular mass in grams. So 1 mole of salt is 58 grams. Let's go ahead and measure 1 mole of salt. Here I am measuring 1 mole of salt. And as you can see, it's exactly 58 grams. Note that the mass of the container is subtracted out. Let's take the example of a liquid. So how much is 1 mole of water? Water has the molecular formula H2O. Atomic mass of hydrogen is 1 and oxygen is 16. So the total molecular mass is 2 into 1 plus 16. That's 18. So 1 mole of water is going to weigh 18 grams. And here I have it ready for you. So I've got 1 mole of water here, and as you can see, it's exactly 18 grams. Let's take the example of a gas like oxygen. Let's say this jar contains 1 mole of oxygen. So what is going to be the mass of oxygen in this jar? Again, we need to take molecular mass in grams. Oxygen has the formula O2. The atomic mass is 16. So oxygen's molecular mass is going to be 32. So 1 mole of oxygen in this jar is going to weigh 32 grams. So on the table here, we have 1 mole of salt, which is 58 grams, 1 mole of water, that's 18 grams, and 1 mole of oxygen gas, which is 32 grams. So as you can see, 1 mole of different substances have different masses because it depends on their molecular mass. Mole is often written as mol or MOL in short. So 1 mole is the molecular mass in grams, and it's also known as the molar mass.
Children, hope You would have enjoyed the first video. Now wait and watch the second video.
Based on molecular mass on our concept board. Mole can not only be expressed in terms of mass, but also in terms of the number of particles. That is, the number of molecules present in the substance. Obviously, the number of molecules is going to be really large, because each molecule is very tiny. So we can't hope to count the number of molecules. We need to estimate it. So if you think about it, how are we going to estimate the number of molecules present in these 1 mole samples? We can use the formula: number of molecules is the mass of the substance divided by the mass of 1 molecule. Let's start with salt. So the number of molecules is the mass of 1 mole of salt divided by the mass of 1 salt molecule. The mass of 1 mole of salt is the molar mass in grams. So it's 58 grams. And the mass of 1 salt molecule is 58. Now this is the relative molecular mass. That means it's 58 times heavier than 1 hydrogen atom. And 1 hydrogen atom has the mass 1.67 into 10 to the power minus 24 grams. If we plug in those numbers and divide, we will get 6.022 into 10 to the power 23 salt molecules. Similarly, we can calculate the number of molecules present in 1 mole of water. The number of water molecules will be the molecular mass of water in grams divided by the mass of 1 water molecule. Similarly, the number of oxygen molecules will be the molecular mass of oxygen in grams divided by the mass of 1 oxygen molecule. So if we plug in the numbers, we will get the same number. In fact, no matter what substance you take, you will get the same number of molecules in 1 mole of any substance. That is 6.022 into 10 to the power 23 molecules. This special number is known as Avogadro's constant or Avogadro's number. In some textbooks you might find it as 6.023 into 10 to the power 23. Let's pin this definition of mole based on number of molecules on our concept board. Now let's take a look. What is the volume occupied by 1 mole of a substance? But remember, this works only for gases, not for solids and liquids. 1 mole of any gas occupies 22.4 liters at STP. That's right, it works for any gas. Now, do you know what is the meaning of STP? It stands for standard temperature and pressure. So standard temperature means the temperature is 0 degrees centigrade, and standard pressure is 1 atmospheric pressure, or the normal pressure that we feel on the surface of the earth. So suppose I set my room to STP conditions. Now the pressure is 1 atmosphere and it's 0 degrees centigrade. So it's freezing cold right now, and just hold on, I need to go and grab my jacket. That's much better now. So let's continue. Let's take the example of a gas like oxygen. So how much volume will 1 mole of oxygen gas occupy at STP condition? That's right, 22.4 liters. So to visualize this volume, I'm sure you've seen this 1 liter bottles of water. So you can imagine 22 of these bottles. That is the amount of volume that oxygen is going to occupy at STP, where we are taking 1 mole of oxygen gas. In fact, 1 mole of any gas, whether it's oxygen, hydrogen, nitrogen, carbon dioxide, they all occupy 22.4 liters at STP. This is called molar volume. Let's put this definition of 1 mole based on volume of a gas on our concept board. Let's say I want 1 mole of oxygen. Since it's a gas, I have all 3 options of measuring it. That is the mass, the number of molecules, and the volume occupied by the gas. So if I use mass, then I need 32 grams of oxygen gas. If I'm using the count of the molecules, then I would need 6.022 into 10 to the power 23 oxygen molecules. And if I use volume, then it's going to be 22.4 liters of oxygen gas at STP. Of course, counting of molecules is impossible. So typically we use mass or volume when we are measuring a gas. To help remember this important relation, you can learn this one sentence. 1 mole of any substance is equal to the GMM, that is the gram molecular mass, and that's equal to 6.022 into 10 to the power 23 molecules, and that's equal to 22.4 liters at STP if it's a gas. Now that we have finished the mole concept,
Hope you would have understood the mole concepts clearly. Shall we move on to the next topic? Dear children, welcome you all to today's session. Let's learn the second topic, Avogadro's law. Watch and learn.
Avogadro's law. Amedeo Avogadro, an Italian scientist, proposed that under the same conditions of temperature and pressure, equal volumes of all gases contain the same number of molecules. Here is an illustration. The law can be explained by correlating the number of molecules present in known volumes of gases. Here we see a volume V of some known gas which contains n moles of the gas. We observe that a volume of 2V or twice the former volume contains 2n moles of the gas. This can be mathematically stated as V is proportional to n, or V is equal to Kn, where K is constant. Now click on the next button. Alternatively, the law can be comprehended as we see here that if 2 different gases are considered of equal volumes and under same temperature and pressure, they will contain equal number of molecules. Now, click on Next for the statement of the law. Equal volumes of all gases under the same conditions of temperature and pressure contain equal number of molecules. Observe the elements and their atomic weights listed on the left-hand side. Though they differ in their atomic weights, they occupy the same volume of 22.4 liters each and represent 1 mole of the respective gases. Also, they all contain the same number of molecules of 6.02 into 10 power 23.
Hi, I am Ram Gopal from Presentation.
Dear children, warm greetings. Have you understood the mole concept? I believe all would have understood it. In this module, let us see the applications of Avogadro's law. Shall we recapitulate the Avogadro's law? Equal volumes of all gases under the conditions of same temperature and pressure contains equal number of particles. Now, let's switch over to the applications of Avogadro's law. First application is, it explains Gay-Lussac's law effectively. Gay-Lussac is a scientist who gave gaseous law. According to this law, pressure is directly proportional to the temperature. The second application is, it helps in the determination of atomicity of gases. Now the question arises, What is atomicity? Atomicity is the number of atoms present in a molecule. The third application is molecular formula of gases can be derived using Avogadro's law. We can derive the molecular formula from the empirical formula using Avogadro's law. The fourth application is it determines the relationship between the molecular mass and vapor density. The fifth application is it helps to determine the gram molar volume of all gases. That is, molar volume of all gases is 22.4 liters at STP. What is STP? It is same temperature and pressure. In our syllabus, they have explained the second and the fourth application. Now, let's see the second application in detail. What is the second application? It helps to determine the atomicity of gases. Consider an equation. Hydrogen combines with chlorine to form hydrogen chloride. One volume of hydrogen combined with one volume of chlorine to form 2 volumes of hydrogen chloride. What does Avogadro's law says? It says about the number of molecules. That is, the volume can be converted into number of molecules. How do we convert? On applying Avogadro's law. One molecule of hydrogen and one molecule of chlorine combines to form 2 molecules of hydrogen chloride. That is, 1 n molecule of hydrogen and 1 n molecule of chlorine combine to form 2 n molecules of hydrogen chloride. If we substitute n is equal to 1, then we all know that hydrogen molecule has 2 atoms. Half a molecule of hydrogen means 1 atom of hydrogen. That is, half a molecule of hydrogen combines with half a molecule of chlorine to form 1 molecule of hydrogen chloride. Hence, the molecules can be subdivided. A molecule is divided into an atom, which is proved by the scientist Dalton. Hence, this law is in agreement with Dalton's atomic theory. The atomicity of hydrogen and chlorine is 2. Now, let's see the fourth application of Avogadro's law. The fourth application gives the relationship between the molecular mass and vapor density. The relative molecular mass is based on hydrogen scale. Relative molecular mass of a gas or vapor is the ratio between the mass of one molecule of gas or vapor to the mass of one atom of hydrogen. Ratio means division. In short, relative molecular mass is represented by RMM. Now let's see vapor density. Vapor density is represented by the letter Vd. Vapor density is defined as the ratio of the mass of the certain volume of gas or vapor to the mass of an equal volume of hydrogen measured under same temperature and pressure. According to Avogadro's law, equal volume of all gases contains equal number of molecules. Let the number of molecules in one volume is equal to n. Then vapor density is equal to mass of n molecule of gas or vapor at STP to the mass of n molecule of hydrogen. Cancelling n, which is common, we get vapor density is equal to mass of one molecule of gas or vapor at STP to the mass of one molecule of hydrogen. Since hydrogen is diatomic, now the vapor density becomes vapor density is equal to the mass of one molecule of gas or vapor at STP to the mass of two atoms of hydrogen. Comparing the formula of vapor density with relative molecular mass, it can be represented as vapor density is equal to mass of one molecule of gas or vapor at STP to 2 into mass of one atom of hydrogen. Consider this vapor density equation as equation number 1. Then relative molecular mass of hydrogen scale is equal to mass of one molecule of gas or vapor at STP to the mass of one atom of hydrogen. This is considered as a second equation. When we substitute the equation number 2 in 1, we are arriving at the formula vapor density is equal to relative molecular mass by 2. Now, when we cross multiply it, we get 2 into Vd is equal to relative molecular mass, or relative molecular mass is equal to 2 into Vd. Children, now we have seen both the applications of Avogadro law. Thank you. Dear children, I hope you would have enjoyed and understood today's session. Thank you very much.